Hello, my name is Nina Samuel. I'm an art historian and historian of science and a curator based at Humboldt University in Berlin at the research cluster Matters of Activity. Thanks a lot for inviting me. I'm very excited to be part of this online conference, which is actually first time I take part in such a conference and the first time ever I record a talk. So please bear with me if the recording is not perfect. It's also a very new experiment for myself. Since many years, one of my focus areas is the interrelation between scientific representations and the formation of theories. You could also say the interrelation between things and the thinking. One area that even after many years I still find extremely exciting is the area of complex dynamics. This is a field that's studied by many different disciplines: mathematics, physics, chemistry, biology, and others. From the mid and late 80s on, this field actually became very, very popular under the buzzword of chaos theory. Here you can see one of the most symbols of this field that has circulated heavily outside of the scientific community. The name is the Mandelbrot set. It's technically just a set of numbers in the complex plane, but it can be used to visualize the border between chaotic and non-chaotic behavior in dynamical systems. As you can see here, it has spread out on cover magazines, on bodies of people as tattoos, as decoration on furniture or t-shirts, or in numerous fantasy depictions. Because of its stunning complexity at its border and the widespread availability of computers, it has quickly migrated into pop culture. But my research is actually not on these kinds of images, but rather on these images. Images used by scientists in their private office, on their workbench, in laboratories that are circulating inside the scientific community. You can see here pictures of Mandelbrot's office from 2011. However, when I looked again at the images in this field as response to the topic of the conference, I actually realized that you could tell the whole story of chaos theory as a story of image circulations. Image circulations are truly structuring its development and its spreading. On top of this, I think complex dynamics is extremely relevant to the question of the conference, as it's a very image-based area. You have mental images, material ones, digital, perceptual ones. There's a whole array of different images that play a big role. And new research questions actually emerge really from these images that are circulating. And second, it's a very interdisciplinary field. So this means we can look at circulations between different cultures of seeing. So now, please come with me on a journey where we can follow selected case studies where circulation takes place and where images are responsible for the emergence of theories and ideas. We see a sheet of paper filled with sketches and notes. The drawing in the upper left is striking: curves and loops in red, gray, and blue, expressively drawn in small arrows, illustrating a development over time. The text relates the drawing to a theory of nonlinear differential equations, and to chaos theory, and to chaotic attractors. The illustration is taken from a notebook of the Japanese engineer and mathematician Yoshizuke Ueda. It was created during his first meeting with the American physicist Joseph Ford in '78, who visited him in Japan. Both scientists belonged to a different discipline, to different research traditions within the theory of complex systems, and they didn't speak each other's language. And look what is missing on the page. There's not a single mathematical formula. Instead, the sketches were used as a universal language, or you could say a visual Esperanto. Thanks to the drawing, Ueda and Ford were able to overcome not only their language barriers, but also the boundaries of their disciplines. Sketching set the circulation of this image in motion. As a result of this meeting, Ueda was invited to an international conference in '79 in the US, where he presented his image to a larger audience. And in the following his discovery, the so-called Japanese attractor became a well-known shape in the mathematical community. At the end of the '70s, conferences became the main circulation points for images in this field. Circulation did not only take place between individuals, but more and more between research collectives and disciplines. Circulation became increasingly institutionalized. From then on, Ueda's image circulated so widely that, by chance, I encountered a huge printout of his attractor in the private collection of the mathematician Bruce Stewart, upstate New York, originally produced in the 80s for the Paris Science Museum, La Villette, Cité des Sciences et de l'Industrie, but for some unknown reasons didn't go on display. However, circulation of scientific images from within the research context to the so-called outside world can never be taken for granted. It's always subject to a very complex network of preconditions and constraints that must be met in order to be set in motion. To find out more about this process in Ueda's case, we must look at the context of the discovery. Ueda had come across this phenomenon for the first time 17 years earlier, during a series of experiments with his analog computer. When he performed his experiments, he actually expected a completely different result, a round shape. And he was very surprised about this, what he called jagged shape or broken egg that he encountered. Because it was such a deviation from everything expected, at first he actually thought this must be a computer bug or a technical error. But as the shape kept appearing throughout the experiments, Ueda tried to convince his supervisor, Chihiro Hayashi, to be able to publish it. But Hayashi was a famous expert in dynamics of the era before chaos. And in his nonlinear world of periodic oscillations, chaos didn't exist and symmetry ruled. You can see an example of his preferred aesthetic here. It's actually interesting that his own aesthetic censorship was so strong that one time he himself in his own experiments encountered an asymmetric result, looking like this, not even chaotic, but just asymmetrical. And this shape was so unpleasant to him that he intentionally left it out from his major publication in '64. The same happened with Ueda's image. Since the broken egg didn't live up to the aesthetic expectations, Hayashi rejected the result and prevented its publication. In his following research report of his working group, he even left it out completely and replaced it with the well-known symmetrical results. Hence, you could say these two crossed-out images here are examples of failed circulation. Up to this point in the mid-60s, Ueda could be called a discoverer without discovery. Circulation was stopped because of a pre-configured way of seeing. What Henri Bergson once stated for the thinking proves also to be true for the seeing. Our mind, quote, our mind has an irresistible tendency to consider the idea it most frequently uses to be the clearest, unquote. The philosopher of science Gaston Bachelard used Bergson's saying to introduce his epistemological obstacle or counterthought. According to Bachelard, such obstacles are necessary preconditions for the emergence of new insights. They constitute a battleground between a creative and a conservative instinct. In this battle, certain what he calls values make the mind sluggish. Questions of standardization form an antipole to circulation, from which new things are born. Well, the question is now, what happened in between 56 and 78 so that eventually Ueda's chaotic shapes could freely circulate beyond disciplinary and language borders? To answer this question, let's look at another image from the symmetrical paradigm from the Hayashi lab and at its transformations. So you can see here where in Ueda's image, you can see what's called a chaotic folding mechanism, so something more asymmetrical. You can see in Hayashi's image, or in the image from his lab, you can see a regular spiral. These structures are actually, by the way, called manifolds. So now what happened that induced a change? If we talk about image circulations in science, we have also to address what I would call the inner or maybe internal circulations, referring to already existing images from other contexts that a scientist encounters during research and that actively influence the thinking and its representations. This happened in '66 when Ueda, by chance, came across an older drawing of the mathematician Norman Levinson from '44. As Ueda states, the drawing made him understand instantly the folding mechanism in the spiral. And this made him then, in the following draw, a mechanism himself in '66 as a corrected schematic drawing that you can see here. In this drawing, it can be clearly seen that Ueda adapted Levinson's folding and rotation mechanism instead of the spiral. Mathematically speaking, this was Ueda's first conscious contact with a potential chaotic topology, where forces expand and contract simultaneously, and by doing so can generate chaos. Levinson's drawing reshaped Ueda's own mental images of the folding mechanism. And finally, with the help of this adjusted drawing, Ueda succeeded in convincing Hayashi to consider other aesthetics than the spiral. In '68, Hayashi published an updated version that you can see here of the spiral form, which incorporated Ueda's construction. The ingenuity of Ueda's new construction lay in a visual mediation between symmetry and asymmetry. His Levinson-inspired scheme was built around a clear center, like the Hayashi spiral, but in its concrete application to the equations, it produced an asymmetrical form, a similar shape that Ueda drew for Ford 10 years later. Also, all these lower drawings actually didn't depict chaos in the strict sense. They opened up the view, sensitized the eye for new forms, and thus created the conditions for the subsequent circulation of Ueda's chaotic shapes through different scientific communities, disciplines, and cultures of seeing. So summarizing this first case study, what can we say? An image that was first judged to be a technical mistake could only be integrated into circulation of science by stressing its visual consistency with existing image traditions on a, I would say, structural level. In this sense, the image had to function as a boundary object. This is a term defined by the sociologists Susan Starr and James Griesemer. Quote, "To translate between viewpoints, we need boundary objects that are both adaptable to different viewpoints and robust enough to maintain identity across them," unquote. Ueda's chaotic shape had successfully become such a boundary object. It had become robust, symmetry-based, and adaptable at the same time, incorporating the new paradigm. This concept is very close to Latour's immutable mobiles. Both notions address the question how images circulate through different disciplinary cultures of seeing, or, to use a term of philosopher of science Ludwig Fleck, through different thought collectives. In these thought collectives, the ability to perceive certain shapes in science is always accompanied by the loss of the ability to perceive others. This explains why certain images might be kicked out of the circulation of knowledge because of aesthetic preferences or assumptions, or why they prove dysfunctional for interdisciplinary communication. However, the challenges of image circulation become not only obvious when a major paradigm shift, like the one from periodic to chaotic oscillation, takes place, but also when a major media shift takes place. To discuss this, let's look at the next case study. In biology, such a media shift happened between 2005 and 2012. A new microscopic visualization technique was introduced, named localization microscopy. This technique was promising to make cellular structures visible that are more than 6 times smaller than the limits of optical resolution. But, and this brings us to our circulation problem, those new and promising images could not be produced by biologists because they usually don't operate these machines in their labs. Instead, those images were produced by physicists specialized in applied optics and information processing. They take commissions from the biologists and take up an intermediary status between two scientific cultures and thus between two different cultures of seeing. So, in which way does this affect the circulation? Physicists need to translate their measurements into forms that are comprehensible for the biological community so that the images are able to circulate. Their challenge is to give the biologists something to see so that they can relate this to their own experience of what cells look like. What this means in practice can be seen very drastically in this example. It's taken from the research of physicist David Baddeley, who discussed the problem how to make this interdisciplinary image circulation work best. He compared 3 different methods to render the data as images that are supposed to represent cells. Here you see on the left, A, the style of older microscopic techniques that the biologists are used for many years. It's called wide field microscopy. B in the middle, a rendering that contains the highest data density and thus the most information. For the physicists, this is the best image. But unfortunately, this B image, the pixelated square-cut appearance, cannot be read by biologists because these patterns simply do not belong to the repertoire that they are used and they are trained to read as biological information. They just don't see any cellular structures in it. So if the data were handed over to the biologists as B, the image would probably cause an interdisciplinary communication blackout. Unable to read it, the biologists might just return the images to the physicists, reports Bedley. Hence, to work properly as interdisciplinary communication device and as a boundary object, the middle pattern B has to be blurred to familiarize the biologist with the unknown. It has to look fuzzier again, and it has to imitate the older wide field images, as you can see here on the right, number C. And be it even with the utmost regret of the physicist about the huge loss of information density. The result is an obvious dilemma and involves a continuous negotiation process between the data and human perception. The aesthetic struggle to find the right form of visualization amounts to an epistemic one that becomes part of the process of discovery, agreement, and circulation in science. Circulation between media shifts requires a visual taming of the unexpected. This means a conscious adaptation of well-known and trained ways of seeing and standardized image traditions. Now I want to move on to a third and final case study that follows up on this question. What happens with circulation in science if we deal with an ambivalent or unexpected result? And in what way does materiality play a role for circulation in an abstract science like mathematics? So let's come back to the symbol you saw in the very beginning, the Mandelbrot set. We now come to its discovery and circulation history in the research context. Mandelbrot was a mathematician working most of his lifetime at the research division in the industry at IBM, but also at different universities. During my research, I discovered 150 graphics like these, produced as experimental series in 1979 at IBM. You can see dots, patterns, and shadows emerge and disappear. Some are just blank, and all bear witness of the difficulty in these early experiments of making anything visible at all. Mandelbrot actually never published them because he was not able to relate these images to any mathematical theory. In some areas, you can already see a vague shape that reminds one of the later famous Mandelbrot set. But at this time, Mandelbrot did not know what he was looking for. This is why he later stated, quote, "I saw it, but I didn't know that I was seeing it," unquote. Seeing and discovering have to be sharply distinguished as two distinct phases of sense impression. The mere availability of the new tool, the computer, was simply not enough. This becomes very obvious during the next research phase that took place during one of Mandelbrot's guest professorships at Harvard. There he had to use what he called, quote, "the most miserable equipment in academia," unquote, referring to the computers available at Harvard in '79. Because of these weak old computers, he reduced the complexity of the formulas and continued with quadratic equations. Before, he had worked on cubic equations. And now, because he used these simpler formulas, Mandelbrot expected a simple result. But what happened was unlike anything he had expected or seen before. The first pictures, quote, "looked awful, filled with apparent specks of dust and dirt that the printer produced in abundance," unquote. The old monitor at Harvard was subject to constant malfunctions, and the rundown printer made it uncertain what one was really seeing. This triggered the important question of how to distinguish between picture and non-picture, between mathematics and materiality. What was dirt and what was visualized formula? What was technical bug and what was equation? The image itself had become suspicious and rose questions about its pictorial status. In order to distinguish between picture and non-picture or calculation error, Mandelbrot decided to examine the specs more closely and to enlarge details. And he found symmetries and small copies of the large shape in the assumed dirt. Quote, Since proper dirt is not symmetric, the specks demanded to be blown up for close inspection. The symmetric points had more chances of being real, unquote. This is how he finally made the discovery of his set, and soon after decided that this discovery is worth to circulate within science. So he performed more research and prepared his first publication on the subject. Starting this circulation, however, was not easy, exactly because of the resemblance of his discovery with these tiny pieces of matter. Because the small specks were deceptively similar to technical errors or printer smudges, they were repeatedly removed by computer lab and print shop employees. For that reason, in the years 80 and 81, Mandelbrot got into the habit of posting warnings on his output equipment. It reads, "Don't clean off the dust specks, they are real." And it reads even in French, "N'effacez pas ce qui semble d'être que des petites saletés sur ce cliché, elles sont toutes réelles et importantes." Despite all his warnings, the biggest disaster happened exactly when his image entered the publication chain for the first time. Here you can see the original computer graphic that Mandelbrot sent to the editors of the Annals of the New York Academy in 1980. You can clearly see the structure of free-floating surrounding little specks. For his reasoning in the article, it was especially important that these little specks were not attached to the main shape. He called them even disconnected portions. But this is how the image eventually was printed in the journal. As you can see, the specks had completely removed by the editors because they were judged as unwanted printing errors. Mandelbrot's reaction was very emotional, quote, "Horrors, it's now free of specks." Clearly, gremlins in the printing business had repeated that evil deed, unquote. Now something remarkable happened with regard to the question about circulations of images. To protest the failed circulation of his image and attenuate the mistake, Mandelbrot was drawing the small specks by hand into the off-print versions of his article that he sent to many colleagues. You could maybe call this practice a microcirculation or counter-circulation, as opposed to the macrocirculation happening through the official publishing houses. But there's also a tragical turn in the story around his first publication. While Mandelbrot had decided to trust the appearance of the disconnected portions as an uncontested truth in the article, 2 years later it was actually mathematically confirmed by French mathematician Adrien Douady that the contrary was the case, that there were actually attached dots by invisible lines to the main shape. But since Mandelbrot did not see any connecting lines during his computer experiments and had unlimited faith in his tool, he did not believe that they existed, and reinforced this again in his drawings that then microcirculated in the mathematical community. One could also say the material side of the mathematical object was more important than the analytical proof. Mandelbrot's famous dictum that was often quoted, "Seeing is believing," changed during these events to "drawing is believing." The digital form had to circulate as drawing to be considered existent and real. Now let me come to some closing remarks. As can be seen in this last example, circulation is a major part of the material knowledge formation in science. For Mandelbrot, his materialized mathematical proof, although wrong in the end, had to circulate to exist. Circulation in science can never be understood by just looking at the history of publications, but one has to take into account the notebooks of the scientists, like in Ueda's case, the counter or microcirculations, Mandelbrot, and the rejected images that are held back to enable interdisciplinary communication, like in the Bedley case. Pictorial norms and conventions function as a solid filter in two directions. First, they influence if a result is taken into account at all or considered as a technical error. Second, they determine the border between the expected and the unexpected, the accepted and the contested result. However, tiny traces or specks of dust and dirt on the interface between the world of thinking and the world of things can be enough to seduce the mind to believe unproven conjectures during these epistemic circulations. All three examples show different strategies how images that break with visual conventions had been integrated into circulations of scientific knowledge and had become boundary objects that are robust and flexible at the same time. First, through an attempt to generate visual continuity on a structural level. Second, through a negotiation process between data and human perception. And third, through an emphasis on visual discontinuity, a conscious break with traditions, but simultaneously relying on the material nature of the mathematical object. All examples show how difficult it can be to maintain a distance between what the eye sees and what can be proven analytically. As the story of a struggle for agreement between observation and theory, the examples illustrate how necessary it is for the eye to be schooled on pictures and to develop a visual literacy. It is thereby revealing not only about mechanisms of circulation in science, but also about the fundamental ambiguity of visual perception. So I've now come to the end of my talk, and I want to thank you a lot for your virtual attention, and want to say that I'm looking forward to the real-time discussion, and say goodbye. See you soon.